Hi, I'm Andy Bennett. I'm here with my colleague Abhinav Chand, and we're going to talk about neural differential equations in an undergrad ODE class. We also have a third author, Nathan Albin, but he can't be with us right now. So I suppose we should get started. We're running a little late. So let's start with what is a neural ODE, and de Kittiger's definition of this is a neural differential equation is a differential equation using a neural network to parameterize the vector field. So we have the canonical example of dx dt as f of t of x. Only that function f will be determined by a neural network. And the reason for this is that, this is a conference about using mathematical modeling, that in some situations, you understand some of what's happening in the model, but there may be aspects that you're not sure about, and you don't know how to properly represent them in the model. And so you can take data and use machine learning to learn what you need for the model there. I remember back in graduate school, back in the early 80s, when fusion was, just 10 years away, as it still is, that one of my friends in graduate school was studying fusion and said, we know all the features. We just don't know which ones are important, and you can't make a model with everything you could possibly think of. And so this is a way of saying, how do you handle when the model has features that you don't understand specifically? And why teach this in an undergrad class? Well, first off, it's preparation. This is an active area of research, and it is very likely to be an important tool long before our students have their careers come to an end. That they're going to need to understand how this works, so they should at least have some exposure to it in their first course, as they're going to use it later. And it also can be very motivating. And I know I'm preaching to the choir here, since this is a conference about teaching differential equations with modeling, but undergraduate differential equations has a reputation as a cookbook course. You learn this equation gets done with this technique. This equation gets done with this technique. And that's not a good thing for our getting students and having them take the course and take it seriously. We want them to see differential equations as this is how you understand systems in various ways. And so having an active modern topic makes the course more relevant in the eyes of the students. And it certainly fits into our students are reading about how AI will change everything. So neural ODEs provide an example where they can see and use AI and understand how it can help, and also understand the limits of what it will help with and what it won't help with. And that's part of our goals in this. So we're not quite ready to say everybody ought to do this yet, because we don't understand it well enough yet. But we are ready to say this can be an extra credit assignment. And the process is to work through a Jupyter notebook to model a spring mass system with nonlinear damping. And this enables us to offload the machine learning to built-in libraries in the Jupyter notebook, particularly PyTorch and Torch Diffie-Q. The goal is to have an assignment that takes about an hour for the students to go through, though if they really know what they're doing, they can probably get through quicker. We'll have 5 two-point prompts. So most students should be able to get the first couple. To get full 10 points, if you want 10 extra credit points, you're going to have to work for it. And you're going to have to really think through these things. That provides extra credit equal in value to one test question. And my experience is if you give such an extra credit right after a test, it's very popular. So our goals are to improve the understanding of the modeling process, to say, how did this work out? How did we start with a situation and build a model, and provide an experience of solving a neural differential equation? How did the machine learning help us? And understanding the advantages and disadvantages of both the traditional and the machine learning approaches. Now, one issue with machine learning is I don't understand it, but Abhinav does. So I will turn things over to him now.
All right. So let me briefly describe the spring mass system. So you have a spring and there's a mass attached to that spring and it's oscillating vertically. So this spring mass system is defined by this differential equation that we study in our differential equation courses. So m times x double prime plus c times x prime plus kx equals 0. X is the vertical position of the mass, m is the mass, c is the damping constant, and k is the spring constant. So you can see that we're assuming that the damping is a linear function of the velocity. So that's why c times x prime. And the spring force is also a linear function, so k times x. And we set out to experiment. So you can see Professor Andy there experimenting with the spring mass system. And we also attached an extra cardboard there just to amplify the damping due to air resistance. So the mass was 500 grams and the cardboard that we used was 37 grams. And we asked the question, can our textbook model fit the data that we get from our experiments? So to get the data, we use this freely available app. It's called the Physlets Tracker App. So it's mainly designed for physics experiments. So what it does is a frame-by-frame analysis of objects that are moving in your video. So in our case, we had to select the mass that we wanted to keep track of. So you select a region in that video, and the app keeps track of that region as the video moves along. And then eventually it gives us the position versus time data, which we want, right? So we get the data from this app, and this is the first question that we pose to our students in this assignment. So we give them the mass versus displacement data. This was measured by hand. And we want them to find the spring constant. So they will make a scatter plot of the data points, and they will find the best line that fits the data. And notice that it does not pass through the origin, right? So Hooke's law does not work
Well,
in reality.
Hooke's law works very well. As the one who took the data, if my physics experiments when I was an undergrad came out like this, I might have had a physics major instead of a physics minor. What it is that when you start with the spring and things are attached, there is a certain amount of work to engage the spring, to get the surface tension of the spring all being coiled next to each other undone. And you have to adjust for that. Well, one of the things we have learned here is that physics is complicated and that actually working with real data is complicated. But again, I think I'm preaching to the choir when I do that at a conference on mathematical modeling. Go ahead.
Right. So this is the linear model, so the textbook model that we use. And we know that it has a closed form solution, x of t equals a times e to the negative beta t times cosine of omega t minus gamma. So you have this sinusoidal decaying function. Beta is c over 2m, that's the decay constant. Omega is the frequency, and gamma is the phase shift. So we used gradient descent to fit the parameters for the data that we have. So on the figure on the left, you can see that in the orange, that's the measured data that we collected. And in the blue, that's the solution that's predicted from this linear model. But we are not satisfied with this picture. So that's why we went with neural nets. So let me explain the neural network part. So first step is to convert the differential equation that we have, the second order differential equation, into a system of first order ODE. So first we have x prime equals v. V is the auxiliary variable, which represents velocity. And v prime equals negative f of v over m minus k over m times x. Now f of v is the damping function that we want. Now in the linear model, f of v is just c times v because it's a linear function of the velocity, right? But what we take here is f of v equals c times 1 plus f tilde of v times v. So f tilde of v represents a perturbation to the linear model, right? So if f tilde of v is 0, you just get c times v, which is the linear model. So we want the neural network to learn this f tilde of v with the data that we have. And as for the K and C, they are initialized for the neural net with values that were learned from the linear model. And at the same time, K is also learned by the neural net, which means that it can tinker with that value as it wants. And this is the architecture. So you have three layers. So you have the input layer, the hidden layer, and the output layer. And these layers are standard ReLU layers. So you have Wx plus b, which is your linear function with a bias. And then you apply this nonlinear activation function, which in our case is the ReLU. And the hidden dimension is 64, which means that there will be 64 neurons in those two columns that you see in that picture. And the loss function is the mean squared error, because this is a regression task. And I will briefly explain how the neural net iterations work. So first, you don't have learned anything. The neural net doesn't know anything. So it just has random values for the weights and biases in those neurons. So then it predicts a value of f of v for a given v. So that's the damping function, right? And in the second step, we use that function, the damping function predicted by the neural net, to generate a solution to the initial value problem. And we use Python's torch diffeq for that. And then in the third step, you calculate the loss. So you have the actual data and the data that's predicted by this model using the damping function. And we get an error, and then we take a gradient step to minimize the loss, and that will give us, using back propagation, we can update the weights and biases of the neural net. And then we continue these iterations 50 times. In deep learning language, it's called epochs, so 50 epochs in the training data. You keep updating, and finally you will get the function for damping that you want. And Professor Andy will explain the results that we got.
Yes. So as you can see on the left, we're closer. We have something better. But then if you look at the predicted damping, the nonlinear damping, that's rather weird. That's not the damping we expected to see here. And if you train the neural net, then this was training on just the first 6 seconds. So you can see the picture's really nice over the first 6 seconds, and then testing against some of the later. If you train on the entire data set, you find something that works much, much better, and whose damping looks a little more like what you expect, that it's linear, close to linear for small velocities, but as you get to larger velocities, you start to observe that no, larger velocities have some nonlinear damping. And if you look at the picture, by the way, it looks a lot like, if you took that damping and you just flipped it down, the left side down, that would look pretty good. We went back and double checked things. That's not what's happening here. This is part of the learning process, that as the neural network goes through, it starts at the blue line, the linear model. And as you process data and go through the epochs, it starts to learn to say, I need to increase the damping, but it increases damping not in the way you would like. If you then take 16 seconds, so sort of 3/4 of the data, it starts to realize, I need to flip this one thing down, and then the thing starts moving down. And when you get to taking the full thing, it starts to say, okay, what I need is an odd function that looks sort of like this. And then that really works. We have tried, by the way, expanding the number of epochs, and by we, I mean Abhinav, and that has a relatively small version of this. And this is one of the things that we want the students to learn, because question 5 is, why do we do differential equations? Why do we learn to solve the first thing? Why don't we just throw it all to AI? And there are several reasons why you don't throw it all to AI and why it is still important to learn the basic differential equation model. One is that you initialize with the learn parameter from that initial linear model. We started with the blue line when we had our thing that we're taking a perturbation, just adding an f tilde of v to our basic linear model. If you don't do this, you don't come close, with this much data. It takes a very long time. And getting data can be expensive, and managing large amounts of data can be expensive. So mixing AI and differential equations reduces the time and data demands, making problems more practical. That here, just having 6 seconds of data, that's 180 data points, wasn't enough. Once we had 20 some seconds, some 600 data points, then we could get something pretty close. And part of what we are doing now is collecting more data to say we want to be able to show the students this is what you get with different amounts. One final point we want is that pure machine learning produces models where we don't know how they work. And they work sort of oddly, that this thing grows and then shrinks and it eventually sort of settles on something. But if you want to understand a situation and the differential equation model helps you understand the situation, then you need to know something about what's going on in there. To say, oh, when things get going fast, the damping is not a linear model very well anymore. When things get moving quickly, you need to have some nonlinearity. If you just throw a machine learning thing in there, you really don't see that. You certainly are not going to have something where you can say there's a qualitative change between underdamped and overdamped. And so understanding these things requires that you have enough to get started, but then you can also say something extra is happening here. I can use machine learning to help fill that in. So what we want to do next is to collect more data, and that's underway, and we're working on how do we do this and set this up. And one thing, so since we're faking you here, we want to actually try this with students in a real class. We got talking about this. Nathan taught the class in the spring and Abhinav in the summer. I should have been teaching in the fall, but I'm on sabbatical. And by the way, sabbaticals are wonderful. I recommend them highly. So we didn't have a chance to use this in the fall, and that's probably a good thing because we weren't ready to really run this yet. But we are working our way through, and we want to say this is something you should be looking at, and this is something you can do. You can find other things online that have some examples that are faked. We think it's important for the students to see real data, that if they're going to model a situation, they need to see a real situation. And that's what we're trying to set up here. But we think that this is a good way to get students excited about differential equations, shows them some new things that they are interested in, that they will use during the course of their career, and helps them understand some of the details of, hey, doing this just all AI, that's going to take an enormous amount of data. The more I can understand this, the better off I'll be. So thank you. Any questions?